Good morning, America. It's great to be back with you guys again. So we're going to pick up here with probably the conclusion of the presentation of the slides on the Rankine cycle review, which should make your heart beat glad. After that, we'll go through some example problems, which I have handed you out copies of. And I'll just talk through them and maybe we review a little thermodynamics, which will get your blood flowing much more quickly, I'm sure, make your heart beat. Pick up your pulse rate. Okay, so this is where we wound up the last recording. And so, now we're going to move into some second law considerations on the Rankine cycle and the various components. As we know, we can talk about these ideal components all day long, but in the real world, things have friction. We have irreversibilities due to finite temperature differences. And so, things don't operate quite as well, not even close to as well as the theoretical, like the Carnot efficiencies and stuff like that. So we'll go through some of these particular subsystems. We know subsystem B is the basic Rankine cycle, steam generation, turbine, condenser, and pump. And then C would be the electric generator that receives the shaft work from the turbine and produces the electricity. D is the heat rejection loop, cooling tower, associated flow rates and pumps. And subsystem A is the actual combustion, where the air and fossil fuel are combusted. And then the exhaust gases go up the stack. Okay, so for our typical coal-based or natural gas-based Rankine cycle, which is depicted over there, the most significant irreversibility is in subsystem A, which has to do with the irreversibility of combustion and the heat transfer. It's the only way we can get reversible heat transfer is to make the temperature difference infinitesimal, which makes the heat transfer area almost infinite, and so we just can't do that. Okay, so then we're going to transfer that heat to make steam in the closed loop B, which is the focus of our discussion here. Irreversibilities occur in the surroundings of subsystem B, and they are classified as external. We have whatever, in thermo, we draw control volume, and anything irreversibility outside of what's inside the control volume is considered external irreversibilities, and then anything inside is obviously internal irreversibilities to that particular subsystem. Irreversibilities in subsystems C and D are also external to our system, to our Rankine cycle in B, but they are relatively minor compared to combustion and heat transfer that go on in the boiler. And we're not going to go into detail, say much at all really about combustion irreversibility, but think about if it was a reversible process. So that would say you could take the products of combustion and run it backward and produce the individual components. The combustion air and the natural gas or methane, whatever, would somehow, we would, I guess, put heat into the system and the reaction would go in reverse. And we know that's probably not going to happen, which means that it's highly irreversible. Okay, so irreversibilities associated with B are internal. We mentioned that. They include expansion of steam through the turbine and the effects of friction and flow through the pump, boiler, and condenser. And I think we could click back up to that very first couple of slides in the presentation on the actual cycles at Kingston. And I would encourage you to do that and just look at the pressure drop. Seems like we had someplace in the neighborhood of 40, maybe 45 pounds of drop on the reheater as that steam comes out of the high pressure turbine and goes back for temperature increase in the reheater sections of the boiler, and then goes back to the intermediate pressure turbine. And so that gives you some sort of a feel for what types of pressure drops that we actually incur in the cycle. And you could look around at the different components. That's the only one that I remember off the top of my head. But it is really of great interest to do that, because, you know, in your Thermal 1 and Thermal 2, you work all these idealized problems to simplify them so that, you know, they don't have to take 10 pages to do. And you gloss over all that stuff. But, you know, if you get out there and when you go to work, that's right down there in the devil in the details of where you do work. And all those things are critically important. So anyway, I would encourage you to do that. Let's see, the most significant internal irreversibility is the expansion through the turbine. And that makes sense because we're going to go in at a pressure 1800 psi G up to 4500 psi G. And when we finally come out of the turbine, the low pressure turbine, we're going to be at about 1 psi A or about minus 13.7 psi G, because it's a fairly hard, not a super hard, but it's a significant vacuum in order to maximize the power generation. And so that's highly irreversible. You know, you can't make that run. You can't try to, you know, get steam to flow the other way through the turbine from this very low pressure to a high pressure. I mean, that's, you know, just common sense tells you that's not going to happen. So that's a significant irreversibility. Okay, isentropic turbine efficiency. Oh my goodness. Now, you guys, you will be tested. You'll be tested on all this, but I can promise you something where you have to calculate an isentropic efficiency on a turbine. And so let's back up a minute and think about these isentropic efficiencies. Okay, these are second law based efficiencies. It's not energy out divided by energy in. If you do, that's what we call a first law efficiency. That's what we do on the boiler. Okay, that's what we do on a lot of components, but that's not what we do on a turbine. And it's because, I mean, you can do that, but if you do, you always get roughly the same number, about 98, 99, 99.5% thermal efficiency on a turbine. It's because they're very small losses. You've got a tremendous flow of energy through that turbine. You've got a high steam flow rate. You have a little bit of heat loss, but they wrap them up with blankets. So the heat loss from the surface is insignificant in terms of the amount of energy that's lost. The BTUs per hour of heat transfer is minuscule compared to the amount of energy flowing through that turbine. Okay, and the turbines are also very low in terms of frictional and dissipative losses. When that steam turbine is spinning at 3,600 RPM in the States, there's no metal-to-metal contact. It is riding in the bearings. Oil flows through the bearings that support the turbine. And as we pick up speed above something like 1,400 RPM, there's no metal-to-metal contact. The thing is floating on a very thin film of oil, and that oil circulates through the bearing. It comes in on one side, goes out on the other side, so it goes 180 degrees around, and then it goes off to a cooler, and cooled oil comes in at that point and circulates around the additional 180 degrees. And so no metal-to-metal contact. You know, we have steam, what we call labyrinth seals between stages and on the ends of the rotor. And unless those things have been wiped, and we'll talk about what that means later, there's very little steam loss through the seals. And so thermally, the thing's extremely efficient. But so we need another type of efficiency to describe the steam turbine, and that is the isentropic efficiency. So basically, an isentropic efficiency is a comparison of a real turbine the work out of a real turbine divided by the work that would come out of an ideal or isentropic turbine operating at the same inlet temperature and pressure. So we put the same steam flow and condition into both turbines. Let's say we get 75 kW worth of work out of the real turbine. We get 100 kW worth of work out of the ideal turbine. We take that ratio and it's 0.75 or 75%. So we say the isentropic efficiency of that real turbine is 75% compared to an ideal or perfect turbine. So anytime you hear isentropic efficiency, it should, a little light bulb should go off in your head and go, oh, this is a comparison of a real device to an ideal device. And then you have to kind of work from there to figure out how you write the equations. But it's pretty simple. If you can get the general concept right, then the rest of it follows just with common sense. Okay, and so here's our equation. And so the isentropic efficiency of a turbine is the work per unit mass out of the real turbine, which is in the numerator, divided by the work per unit mass of the ideal turbine. Okay, and if you look at the TS diagram over there, so the turbine expansion, this is showing saturated steam into the turbine at 0.1. And so the ideal turbine is going to drop straight down at constant entropy, isentropic, to 0.2s. And so basically, if you know 0.1 and you know the lower pressure, you just go to the steam tables and you have to do a little work in the steam tables because it's, two-phase. But so you know the entropy at 1, so you know the entropy at 2, and you know the pressure. So you can calculate the enthalpy at 2. You can calculate the quality, I'm sorry, at 2s by going straight down. And then to get 0.2, because the real turbine has irreversibilities. And so you get that dash line. They usually draw a dash line because it's a little bit of an indeterminate process line. I mean, does it, but it doesn't matter. It just kind of indicates that it's not a line of constant this, that, or the other, because you've got entropy increasing. And, different turbines would wind up at different states too. Some may have more entropy generation, more friction, more irreversibility than others. And so 0.2 can slide back and forth a little bit on that isobar line of constant pressure where you have to stop because you're saying we're going to come out at the same pressure. If I have a better turbine, then I will approach a vertical line straight down. And as you move along that line to the left, the enthalpy gets less and less because you have less steam and more liquid. And so you're saying you get more work out. So the maximum possible work out is in the denominator, H1N minus H2S out. Okay, and so I think all that pretty well follows. The other thing to note is that the real turbine, the blades are happier at 2 than they are at 2s because there's far less moisture. Well, I don't say far less, but there's less moisture. The quality is higher at 2 than 2s, indicating that there's less moisture, indicating that we're not beating the blades up as much as they rotate around the wet sections of the turbine. Wow, that's a long time on one slide. Okay, so I think I've said all this. Yeah, oh, this is good. So you can see the depiction of this. And if you don't really understand this, I'd say listen to this particular description on this slide, and then go back to your thermal book. There'll be some examples in your thermal book to show you. Okay, pretty good. Okay, well, pump work input is much less than turbine work output because we've seen the back work ratio for the Rankine cycle is 1-2% typically. Depends on the particular cycle, but it's very, very low. But there's still irreversibilities in the pump, friction, turbulence, all that sort of thing. And so we need to look into it a little bit. Okay, so on the TS diagram, you see, so the condition going into the pump is state 3. The isentropic pump, obviously, again, now it's a line of constant entropy going up until it hits its discharge isobar. And so the line 4S, 4 up to the dome and over to 1 is all at constant pressure. That's the isobar. So, in reality, let's say at Kingston, the steam pressure is nominally 1800 psig. So that's 1815. They call it 1814.7 or 1815. The power plant people usually just go ahead and call atmospheric pressure 15. But so let's say, so that isobar is probably in the order of 2000, 2100, maybe even 2200 coming out of that pump. So that's what really establishes the high pressure in the system, is what we come out of that feed water pump at. And then it goes to the boiler. And of course, in the ideal cycle, we say we would just come out at 1815 psia or 1800 psig, and we have no pressure losses. But in the real cycle, yeah, we probably have to come out 200 to 400 psi greater in order to, move everything through the boiler and get the steam out into the system. So anyway, but the ideal pump is going to operate from 3 to 4S, and the real pump is going to generate some entropy. So that line has to be to the right of the vertical from 3 to 4S, indicating that we have some entropy generation. We also come out at slightly higher temperature. Now this is blown out. This is not necessarily the scale, but they have to, draw them far enough apart so that you can see the concepts on the diagrams. So 4 and 4S have the same pressure. 4 has a little more temperature, and that's because of the frictional and dissipative effects of the flow through the pump. Okay, that's pretty good. Let's see. Okay, so now note that the ideal pump is on top in the efficiency, isentropic efficiency of the pump definition, and the real pump is in the denominator because it's an efficiency, and this is typically runs from 0 to 1. And if you think about it, and so a pump has work input to it. Well, remember the turbine had work output, and so that put the ideal turbine in the denominator. But in this case, if it's a work consuming device, the work consumed or required is going to be in the numerator, because the real pump is going to require more. And so we have to flip the definition, if you will, to make this thing come out between 0 and 1. And so because the real pump is going to require more work than the ideal pump. And so other than that, this is work input per unit mass flowing through the pump. And so you see for the ideal pump, that's going to be H4S minus H3, and it's written in that order so it gives a positive number. Because when you go through a pump, the fluid is going to have more energy exiting than entering, because the pump did work on the fluid to increase mostly its pressure and its temperature a little bit. Okay, and so then that isentropic work is divided by the work out of the real pump, was at H4 minus H3. Okay, hopefully that's clear to you. Okay, we'll put the little tags on there so you can look at this. I think I've described it pretty adequately. There we go. There you go for the isentropic, and there's the process line. Okay. For simplicity, frictional effects resulting in pressure reductions from inlet to exit of the boiler and condenser are ignored in Chapter 8, which is what you did in the thermo. So we may have some problems. I mean, as far as the problems are concerned, we just have to tell you what the pressure drop is, or what the pressure coming in and going out of any particular component is. And it's just a, the complication is that you just have to look up some additional thermodynamic states. So it's not really a big deal. It just makes the problems longer. Okay, flow through these components assumed to be at constant pressure, and you should assume that unless you're told otherwise in working a problem. Okay, feed water heaters. Another method for increasing thermal efficiency of the vapor power plants is by the application of regenerative feed water heaters. So when we start using feed water heaters, that, the thermodynamic term is regeneration. And basically what regeneration is we're going to move some energy around in the cycle to preheat the feed water coming out of the condenser with any makeup water that we had to put in there. We're going to try to boost that temperature as high as we can before we put it in the boiler. Because the average temperature, if we increase the average temperature during the heat addition or the heat transfer into the working fluid in the boiler, we will increase the overall thermal efficiency of the cycle. We talked about that earlier. Remember, if we increase the average temperature during the heat addition, we increase the cycle efficiency, keeping the condenser temperature the same. Or if we keep the heat addition the same and lower the average temperature during the heat rejection to the river, the lake, the air, wherever we're dumping the waste heat, that also increases the thermal efficiency. So it turns out it's easier. It's just you have to buy this additional hardware, and we extract steam from the turbines, which reduces the power output of the turbine certainly, but there's more bang for the buck in terms of the reducing the cost and improving the efficiency to take that steam, throw it into a feed water heater, condense it, and increase the temperature of the feed water. Excuse me. Before it enters the boiler. So that's what this regenerative feed water heaters is all about. And so once we start doing that, some books call it just the regenerative cycle. Other books call it the regenerative Rankine cycle. I typically call it the regenerative Rankine cycle because I want to make sure that people realize it's still a Rankine cycle, but we're buying extra hardware in order to make it more efficient. And that's the regenerative portion of it. Okay, regenerative feed water heating increases the average temperature of heat addition, thereby increasing thermal efficiency. Okay, we said that. Okay, they're both what we call open and closed feed water heaters are typically used. So a closed feed water heater is just a typical, it's big. Now and I may do this, I may pull out some pictures of this and show you what these things look like, but it's a large shell and tube heat exchanger. And the extraction steam comes through on the shell side, and the feed water is in tubes. And it's simply, the steam and the feed water do not mix. So the steam condenses on the outside of the tubes, the heat goes in, heats up the feed water, the condensate falls to the bottom and flows backward or flows to a lower pressure feed water heater, or in some cases, depending on where it is in the cycle, it may have to be pumped. But anyway, the condensate the steam condenses in the heat exchanger, and basically we have pretty close to saturated liquid coming out the bottom. It gets, we don't throw it away, we retain it in the cycle. So, but the open feed water heater, they actually mix. An open feed water heater is called a deaerating feed water heater. And the purpose of that is to strip off any oxygen or non-condensable gases that may have come into the system, probably with the makeup water. It's possible to have, some air leakage into the condenser, which some of that can get pulled up into the condensate. But anyway, oxygen at high temperatures is extremely, will cause corrosion, pitting, all kinds of things. It's very corrosive. And so we have to be careful that we don't allow any significant levels at all. I mean, it's in the part per billion range. I don't have a number off the top of my head but it's very small. So we strip most of it out in the deaerator, and there's often some chemical addition. There's some chemicals that are called oxygen scavengers that will grab onto any oxygen molecules that might be left in that feed water and bind them up chemically so that they are not corrosive. So we typically just have one of those per cycle, and it'll be kind of at the mid pressure range. And we can go up here in a second and take a look at where those are in the actual Kingston cycles. But there, so the steam that comes in and the water actually mix, and so then the steam condenses into the water as it strips off. It falls down to the bottom and goes out. A DEA has to have a small vent in order for a little bit of steam is vented, and then that pulls out the non-condensable gases, and that'll exit up through the top of the deaerator. We can look in those cycles here in a little bit and see if we can trace that out. Okay, so this is what we get into on the regenerative cycle. So now, and notice on this, we have these little numbers in parentheses. So where we come out of the boiler, we have that arrow pointing toward the high pressure turbine or the first section of the turbine, and we have that 1 in parentheses. So that 1 means that we have the entire mass flow. I call it main steam flow, usually out of the boiler. So that's the maximum steam flow in the cycle. And so we enter the turbine on the left-hand side. We expand, say, halfway through the turbine to the extraction port. And then coming out of the bottom of the extraction port at 2, we have an arrow pointing, kind of downward at a slant. And there's the parentheses with a Y in there. Well, so that Y indicates the fraction of the main steam flow that is extracted at that point that's going into that open feed water heater. Okay, so just to have some numbers to talk about. So the number is 1.0, obviously indicating we have all of the steam into the high pressure turbine. And let's say the extraction is 20%. So if we had 1,000,000 pounds an hour, when we get to 2, we'd be taking 200,000 pounds an hour and pulling it out and sending it to the open feed water heater. So that's the Y would be 0.2. So then from that point on, from 2 to 3, going through the turbine, well, we don't have 1,000,000 pounds anymore. We pulled 200,000 out at 2. So 1 minus 0.2 is 0.8. So so that's the fraction, or it's 80% of the steam flow can generate power from state 2 to state 3. And so the power generation is what goes on with the full steam flow from 1 to 2, plus the power generation from 2 to 3 that only has 80% of the steam flow to push it. So, we get a little bit reduced power out, but we get to boost the feed water temperature significantly. We might pick up, 40, 50, 60 degrees in temperature going through the open feed water heater, and that improves the cycle efficiency significantly. Okay, so that's why we do it. Then if we trace the steam flow on around the cycle coming out of the turbine at 3, well, how much steam do we have? So we use these little symbols in parentheses, 1 minus Y, to indicate so that we can remember how much steam is flowing through the condenser. So if we had 1,000,000 pounds an hour out of the boiler, we only have 800,000 pounds an hour going to the condenser, which has to be condensed. Okay, and so you see the Q dot out, that is actually accomplished by, river water, lake water, or cooling tower water that's pumped into and out of the condenser, picks up, 10 to 20 degrees in temperature, and takes that heat out and dumps it to the environment, either the lake or the atmosphere. Okay, so then the condensed liquid at the condenser pressure falls into pump number 1. We have to put, some work into, so that's W dot P1 goes in. We come out at 5, and then we go into the open feed water heater. The steam comes in, and that is basically mixed together. This doesn't show a vent. I mean, the vent, as far as thermodynamically, the vent is insignificant. it's a very small amount. But as far as, you know, controlling the corrosion levels in the cycle, it's critical. So you got to have that. We call it the DA for deaerator vent, comes out. Some cycles throw that away. Other cycles will put it in a heat exchanger or take it someplace to retain the energy in the cycle, and then somehow you got to get the air, nitrogen, or whatever came out, get it vented. And so all that mixes together, and we come out at 6, and then we go into another pump. So anytime you have an open feed water heater, you have to have a pump after it, because that open feed water heater is going to operate basically at the pressure of the extraction at number 2. And so that's going to be way, way less than boiler pressure. And so that's the pressure in that can basically that's coming out the bottom. And so you got to have a pump. Once you get it out of there, even if you have additional feed water heaters, all of the feed water is enclosed in pipe. And so then you can just come up to as high pressure as you need, so long as the pipe's strong enough to hold it, to force it into the steam generator to get you the pressure that you need entering the steam generator to make the boiler work, okay? You can look at all of this, and you should study it on the TS diagram. So 1 is up there. So now we're showing superheated steam at 0.1 at the high pressure, the high isobar. And so we're showing an isentropic turbine here, right? Because we're dropping straight down from 1 to 2. And so that enthalpy difference, H1 minus H2 times the full mass flow, is going to be the work that's generated in that section of the turbine. So then we're going to tap out some steam at 2, which is eventually going to mix with water that's going to wind up over there at 6. And so we're assuming all that happens at constant pressure. In reality, there would be some small pressure drop through that. The remaining steam in the turbine, which is now, in our little example, 80% of the main steam, is going to continue through the second section, or you could call it the low pressure section of the turbine, whatever. You can think about it as 2 different turbines, or you can think about it as 1 turbine with an extraction port. But the pressure continues to fall. So from 2 to 3, again, that's isentropic. And so the power generated from in that second section of the turbine is H2 minus H3 times whatever mass flows through there. And so for total turbine work, you would have to add those together. And then we come out and we have to go through the condenser, which we're showing as constant pressure. So we have a significant amount of moisture coming out of the low pressure section of the turbine, the end of the turbine. And so we condense from 3 to 4. And then we have an isentropic pump from 4 to 5. And then we do our feed water heating from 5 to 6, another pump from 6 to 7, which gets us back. Now, so the point of all of this, point A is where we would have entered the boiler had we not had the feed water heater. So that would be temperature A. We would have exited at temperature 1. And so you can see the average temperature between A and 1 is far less than the average temperature between 7 and 1. That's why we put the feed water heater in, to increase the average temperature during the heat addition, which increases the cycle efficiency significantly. So that's what feed water heaters and regeneration is all about. And just remember, we have open and closed feed water heaters. Ooh. Okay, so let's see. I think he's going to talk through. Yeah, we're going to go around the cycle here. So I'm not going to do it again. Probably should have just done it a slide at a time, but that's too bad. So, the first is the turbine he's got outlined in the red. And so we talked through that previously, so you should understand what's going on there. I guess these are some of the assumptions. So we're assuming no pressure loss through the condenser or pressure changes, and also the steam generator. Mixing, that's irreversibility, by the way. So this is still part of the second law discussion, but you can't get that stuff to flow back out in the other directions and come back apart, which means it's irreversible. That's good. The feed water heater is assumed to operate adiabatically, which we're not allowing for any heat losses. We insulate it real well so that there's no heat loss. Okay, so let's see. So TS9 heat transfer to the cycle takes place from state 7 to state 1 as opposed to A. Yeah, so we talked about that, which would be the case with no feed water heater. Open or open. Okay. Oh, okay. And so there, we can do that. So because of this, we're running from 7 to 1. So the average temperature during the heat addition increases and the cycle efficiency increases. So that's what it's all about. There's T average from A to 1, and then T average showing much higher from 7 to 1. So that's why we add the feed water heater. Okay, now we're going to trace a unit mass as it moves through the cycle. Okay, the unit mass is denoted by the parenthesis 1, and in my description, that's the entire main steam. That's the maximum main steam flow out of the boiler. Like I said, it could be 1,000,000 pounds an hour. Okay, the unit mass enters the turbine at 1, expands, creating work, goes into the shaft where the fraction Y is diverted to the open feed water heater. Oh, I love this. That's pretty slick. That's so much fun. Let's do it again. I like this stuff. I don't know who wrote this stuff, but this is pretty good. Okay. So we took our 20%, or it depends on what problem you're working. It could be 10%, it could be 15, it could be 25, whatever. It doesn't matter. So the remaining fraction, 1 minus Y, expands through the second turbine stage to state 3 and is condensed to state 4 and then pumped to state 5 where it enters the open feed water heater. Okay, let's do our little, all the way around. I'm a simple-minded individual. I love these. I think this is pretty slick the way they program this. I'm not good enough to do that in PowerPoint. Anyway, so okay, so the fractions Y and 1 minus Y entering the feed water heater states 2 and 5 mix and giving, so then the steam flowing out, the amount of steam flowing out at 6, it's Y plus 1 minus Y, which is 1, which tells us that we put the entire steam flow back together. And so we have full main steam flow coming out of the feed water heater. Yeah, that's good. Mix them together and it turns into, oh, that's just so cool. Mix them together in the feed water heater and we come back out at 1. Pretty good. So the unit mass or the total mass flow, however you want to think about it, 1 at state 6 is pumped. We're going to pump it into the boiler where it after heating. So then that takes us all the way back around the cycle. So that's good. So hopefully that's clear to you now. These problems aren't really that much harder, but you just have to keep track of. You always have to ask yourself, okay, how much mass do I really have? If we were doing a energy balance on a feed water heater, and you say, okay, now how much mass is in here? How much mass is in here? Do they mix? What comes in? What goes out? And just write the fairly simple equations correctly. Okay, so applying steady state mass and energy rate balances to the control volume of the feed water heater, the fraction of the total flow Y is, and let's see. So what you do is you just draw a control volume. I don't think that gets shown specifically in the slides. But if you go back, let's go back and just Okay, so if you draw a control volume around the open feed water heater, what do we have? So coming in the top, we've got Y indicating the mass fraction in times H2. That's the enthalpy of the extraction, 2, and that's coming in. We also have the mass flow for coming out of pump 1 going in. So that would be, so when you write the equation, you put the summation of the mass flow times the enthalpies coming in is equal to summation of the mass flows times the enthalpy out. So we've got Y times H2 plus 1 minus Y, parentheses, times H5 is equal to 1 in parentheses, which doesn't really have to be written, times H6. And that's your energy balance on the open feed water heater. And the mass balance is Y coming in plus 1 minus Y coming in is equal to the sum of that, which is 1 going out, which just tells you that you put your mass flow back together again. So that's what they've done in order to come up with this. And then you just, solve the equation for Y. You should do that on a piece of paper. It won't take you, 60 seconds probably. And so that's that. When we work these problems, and if you're not given these extraction amounts, then you have to go back, and you always go to the high pressure heater first. That will be the easiest one, and then you work your way down in pressure. Because some of the lower pressure heaters may have some of the other extractions involved. The high pressure heater will only have one extraction involved, and you've got all of the mass going in the feed water put back together. So that's the rule of thumb. Okay, with fraction Y known, mass and energy rate balances applied to control volumes around the other components will yield the following expressions. Okay, so this problem is pretty easy. I mean, if I give you one with 4 or 5 feed water heaters, then you got a fair amount of calculating to do. But it's not very hard. It's just long. You've got a lot of different states to worry with. So the total turbine work, and we scale that turbine work per unit mass of the main steam at 1, m.1. Okay. And so, if you want the total turbine work, you just multiply that equation through by m.1, and that gives you the absolute value of the total work. This is going to give us the work per unit mass entering out of the boiler or into the high pressure turbine, just by convention. And so we get H1 minus H2, but the 1 minus Y accounts for the fact that we don't have all of the mass through the second section of the turbine. So we get 1 minus Y times H2 minus H3. So that should be pretty clear. You can do a mass balance around or an energy balance around the turbine and come up with the same expression. Okay, so for the pumps, we do the same thing. So for for pump 2, we have the entire flow put back together. So its coefficient out front is 1, which they don't write in that equation. So it's just H7 minus H6 is the pump work per unit mass. And then for the pump P1, it's H5 minus H4, but we have to multiply by 1 minus Y because that accounts for the fact that we don't have the full mass flow through that pump. So it doesn't have to work quite as hard because it has less mass to push. Okay. And then, so for the steam generator, now here, see, we don't have reheat put in here yet. So we just have one heat transfer section in the boiler. So it is just the heat added to the steam per unit mass is just the exit enthalpy minus the inlet enthalpy. So that's pretty simple. But for the condenser, again, we don't have full mass flow through there. So that's 1 minus Y times the enthalpy difference across the condenser, H3 minus H4. Okay, there we go. Okay, so we'll go over some example problems here in a little bit. Um, there are integrated systems that simultaneously produce two valuable products. Usually it's electricity and thermal energy in the form of steam, which can drive other things in a process. So industries, large industries oftentimes do this. Refineries, I go to a lot of plants that have cogeneration type systems. And so the idea is that we combust a fuel, natural gas or coal or oil or something, to produce the heat. We make the high pressure steam. We generate some electricity going through a turbine, and then we come out. In these systems, we typically come out of the turbine at a much higher pressure, a pressure high enough that it has enough temperature that it's useful for doing something else. So we can then take that steam out to a process, make our product. And so instead of throwing away energy in the condenser, we condense that steam in heat exchangers that are making a valuable product for us. And so we get a much higher cycle efficiency. We can see cogeneration system efficiencies as high as 65 to probably pushing 80%. Not probably many quite that high, but easily 75%. So we want to talk more about that. Okay. So this typically provides cost savings relative to producing the power and the steam independently. Because what would happen if the industry was not doing cogeneration, they would just be buying their electricity from the power company, who would be 32 to 35% efficient, most likely, throwing away 50% of the energy that they combust, that they get out of the fuel in the condenser, because they don't have a use for it, because they pull that their exit turbine pressure down so low that the temperature is like 105 to 115 degrees, and you can't do anything with it besides throw it away. But the industry, if they cogenerate, they get electricity and they come out of their turbines with higher pressure steam that they can utilize. And so they don't throw away all this big bunch of waste heat. So it's a much better way to go. It just has to be designed into the system. So these are widely deployed, industrial plants, refinery, food processing, etc. So it can be the Rankine cycle, it could be a Brayton cycle, internal combustion engines or fuel cells can do all of this. Okay, an application of cogeneration based on vapor power plants is district heating. They do a lot of this in Europe. The land areas are much smaller, and a lot of times the plants are much closer. And so, a plant, industrial plant or something, may come out of the boiler with high pressure steam, go into a turbine, and then come out at, in the US, maybe 200 psi, maybe 100 psi. 100 psia is about 327 degrees, which is plenty warm enough to heat your house. So then what they would do is put that into a heat exchanger, make hot water or steam. A lot of times they'll just make hot water and pump that out, or they may distribute steam out to a neighborhood, and people heat their homes with it. And so that's very good. Or it could go to the plant for additional use. Okay, steam exported to the community, electricity exported. And so we're getting two products out for one fuel source, cogeneration. Let's see. For instance, to produce saturated vapor at 100 degrees C, 1 atmosphere, condensed at a higher temperature. And yeah, so that's what they're talking about, coming out at a higher pressure here, so that you have enough temperature to be useful. I think that's what it is. Yeah. So, and that does limit the amount of power generation, but you get to use all this thermal energy as well. So I think we've talked about that. You can. Okay, we're just about done here. This is, I took a trip to China a number of years ago, and we were looking at some systems they were proposing to build. They wanted an expert opinion, which turned out to be me, I guess. But anyway, so this was at a big industrial park, and this is kind of cool. So what these guys were doing is this heat gas came out of a chemical process. So this is gas they had to get rid of. They had to use one way or the other. And so you can see the flow rates. This is normal meters cubed per hour, that sort of thing. And so they would put it into a compressor because we had to get some more, and these are just silly little icons, but they're not exactly what the real equipment looked like. But so we had to boost the pressure a little bit, and then it was combusted in a gas turbine, which produced here, and you see the flows, but this is 11 megawatts. Of course, in terms of a TVA unit, 200 megawatts is small, but 11 megawatts is a pretty good amount of power. Okay, so we come out of here with hot exhaust gases at 488 degrees C, which, that's about 1,000 Fahrenheit or more. So, and this is a hot oil generator. So what they're going to do is they're just going to take these hot gases, put it in this hot oil boiler, or something to boost the temperature. So the hot oil is coming back from industrial processes at 295 C, and it's heating it up to 330 C and putting it out. And here we had to combust a little bit of additional heat gas, which they had plenty of, so that was not an issue. Okay, and so this comes in, we do a little combustion, we heat the oil up, what is that, 35 degrees C, which 35, 70, probably 65 Fahrenheit, goes out to the process. So we take exhaust gas out of this at 330 and we put it into a steam generator. And so we're putting in liquid boiler feed water at 105, and we're producing saturated steam at 0.6 megapascals, and that's 7.7 tons an hour. Well, a ton is 2,200 pounds, US pounds an hour per ton. So, I mean, that's a significant steam generation. Okay, but we're not done yet. So then they're going to come out of here at their exhaust now is down to 175 C, and they're going to put it into a hot water generator. And so they've got 90 degrees C hot water, return water. That's the cold water coming back. And it's going to be heated to, 130 C. And this is going into an absorption chiller, which is a refrigeration device that runs on heat. And so they've got 12 degree return chill water, 300 tons an hour, that's being chilled down to 7 degrees C, that's going out. And this is condenser water that's coming in. So they have to, these things have to dump some heat from them. And then the final exhaust gas is 115 C. So out of a waste product, they're getting 1 power, 2 hot oil, 3 steam, and 4 refrigeration. So this is quad generation. So this is pretty good. This is, you can't, my goodness, for a thermal efficiency guy, this is pretty darn impressive. So anyway, I just thought you might want to see that. Okay, and exergy, I'm not going into exergy. That's more second law stuff. So I'm going to stop the presentation here, and my next one will be going through the example problems, which we'll get that probably posted later today. Okay, so thanks very much for your kind attention.